Hello. We are now ready to complete our discussion of chirps, which we started on Friday. Now what's that? Just like the sound a bird makes or what? Well, mathematically it means something a little different. So we'll dig into that, but we'll see that we can indeed make some pretty cool sounds with this. Okay, but to do chirps, we have to first remember what is a sinusoid. And this should be old hat by now, but just to make sure we start off on the same page. That is a function y of t, which is cosine of 2 pi f t plus some phase offset phi. So there's my sinusoid. Okay, now let's define a chirp, which is actually just a more general version of a sinusoid. So a chirp is defined as y of t equals cosine of 2 pi f of t. And that's it. Now it looks like all I did was just change some symbols around. Like, what's really different with this other than it's missing the phase? Well, actually, I want to think of f of t is some arbitrary function of time. Okay? So, for example, just to show you, a sinusoid is a chirp. Why? Well, because I can construct a function f of t, which is at plus b. So if I choose any linear function, any line, sorry, not a linear function, that's something a little different, any line, at plus b, then what I'll find, if I plug this into the definition of a chirp, that gives me yt is equal to cosine 2 pi times the quantity at plus b. And if I expand this, I see, well, that's actually equal to the cosine of 2 pi at plus 2 pi b. And what I notice then is that, yes, that's a sinusoid where the frequency is a, and the phase offset is 2 pi b. Okay? So cool. I just defined something more general than a sinusoid because I was able to construct a sinusoid in the framework of a chirp. Okay. Alright, so we got our chirps, but we can do more than that. Sorry, I want to make these nice and big so they stand out. Sinusoid and chirp. We can certainly go further in this though. So let's look at another example. What if we say f of t is 440 t squared? So I'm going to bring stuff into the audible range now. Okay, f of t is 440 t squared. Let's go ahead and just listen to this. Because what we're going to get is this chirp, y of t is equal to cosine of 2 pi times 440 t squared. Alright, so let's listen to it. So I'll say t is equal to np.a range. Maybe we'll listen to 2 seconds. We'll say the sample rate is 44,100. And I'm saying y is equal to cosine 2 pi 440 t squared. IPD dot audio. Oops, I need to also import all my stuff. Import ipython.display as IPD. Alright, so I say audio y rate equals SR. So let's listen. Okay, interesting. So this went up in frequency, unlike a sinusoid, which always is the same, right? Okay, so already that's a little different. What if I try the following? And actually, I'm going to back up and just do this for over 1 second for now. Okay. 1 second of this. Let me now say that I have a different chirp. So I'll say f of t is equal to 440t cubed now. So, you know, it's the same thing. I have y of t is equal to cosine of 2 pi 440t cubed. And so let's listen to this. So I'll say y2 is equal to that, t cubed. Listen to these two side by side. So what's interesting that you notice is that this one actually ends up higher. Okay. And let me just do one more step here. So I'll make this, I'll say y3 is, let's just do t to the fourth. Okay. Okay, so that one went up even higher. Now what's maybe a little bit surprising about that is the fact that if I go to plot these functions f of t, then I will see that, okay, so let's go ahead and do that. So plt.plot t squared first, t cubed next, t to the fourth after that. Okay, so we got t squared, t cubed, and t to the fourth. I got to remember that actually this is 440 times that. So let's look at this. So what we see actually is, okay, so over the time interval, so it's t, I'll say time in seconds. Between 0 and 1 seconds, all three of them start off at 0 and they end up at 440. So it's a little bit surprising maybe if you try to use the intuition from a sinusoid that they would end up at different frequencies, because it looks like this function, like the inside of the sine, ends up at the same place. But this is where we get into not just frequency, but something called an instantaneous frequency. Okay. So we actually hear something called an instantaneous frequency. And it's simply just the derivative of that function with respect to time. So instantaneous frequency is simply this. The derivative of that function with respect to time. Okay, and so that's actually the frequency that we hear. Now if I go back, let's look, okay, what examples can we look at? So if I go back to looking at an example like f of t is equal to 440 times t, then I can see, remember this is a sinusoid, right? I just plug it in and this will give me 2 pi 440t. Well, the derivative of this is a constant, right? So now I'll use Newton notation instead just to make it easier to type. So the derivative of this is a constant. So that's how we see like an ordinary sinusoid, where you just have a line for your f of t. That is a constant frequency. But if we switch that up and we go to f of t is 440t squared, well, in that case, we use the power rule for the derivative and we get 880t. So what we see is two things. Number one, this actually grows. The frequency goes up over time. And the other thing is, because of the power rule, we actually brought back down a factor of 2. So even though it looked like this function was ending up at the same place, its derivative is higher at the end. Okay. So you can see the slope of the orange curve is actually twice the slope of the blue curve. And then similarly, if I go to the cubic function f of t, then I see that that the derivative is 1320 t squared. So this explains a few things. So if I go and I listen to these, so here's the t squared. So first of all, I can hear it starts off at kind of low, but it ends up, it should start off at 0 actually, because 440 times 0 is 0. Okay, but it ends up at an octave above 440, which should make sense. So here we go. So this ends up an octave above 440. The cubic one actually ends up at 1320, which is 3. That's the third harmonic. Or, yeah. So we go 440, 880, 1320. So the second harmonic, sorry. But this is a fifth, actually, of the note corresponding to 440, or it's a fifth of, is actually the fifth of the octave here. So we got this. So this one ends up at a fifth of this. And this one's actually going to end up in an octave of the first one. Because if I take the derivative of the quartic here, t to the fourth, then I get 1680 t cubed. So I see in each case they're growing faster. So I hear the frequency is increasing faster, but I also am showing you that at time t equals 1 they end up at higher places because their slopes are higher. Okay, so we hear the slope. That's the bottom line. So that's pretty interesting. Now, okay, so one thing, let's expand on one of these examples a little bit. So let's say, so we can actually use antiderivatives to do designer frequencies. Okay, so let's say I want to start at 220 hertz and end at, let's say, maybe we'll go through 3 octaves, so 1680 hertz over an interval of 3 seconds. Okay. So what I'm saying is, all right, so let's just write down what the f of t would be. So I'm saying f of t should be 220 plus 1680 minus 220 I guess we'll say times t over 3. Okay. So when t is equal to 3, then this will be 1680. When t is equal to 0, it'll be 220. So in order to find, so actually this is the derivative, right? Because we hear the derivative. So our instantaneous frequency should be this. This is what we want. Now to get back to that f function, I have to take the antiderivative. So that ends up being 220t plus, okay, hang on, 1680 minus 220 is 1460. And that is times t squared over 6, actually, right? Okay, because that was, when I do the antiderivative, I bring down a factor of 1/2, and then it was over 1/3. Okay, so this is the function I should be using on the inside of the cosine to do this. And no, okay, look, if you're being really pedantic, there's a plus c here, right? The antiderivative includes plus all constants. That's just going to be a phase change. It doesn't actually matter for what we're listening to because this thing oscillates very quickly and it doesn't interact with other things, so it's not going to make beats or anything like that. So anyway, okay. But let me do this. So I'll say sample rate is 44,100. T is equal to np.a range SR times 3 over SR. And then I'll say F is equal to 220T plus 1460 times T squared over 6. Okay. So let's listen to that. And then I'll say Y is equal to cosine of 2 pi times that frequency. And then I'll say IPD.audio, Y rate equals SR. So I went through 3 octaves there, actually. I started off at 220, then I went to 440, then I went to 880, then I went to 1680. Okay, now, but this, as we talked about in class, we don't perceive pitch linearly in frequency. We actually perceive pitch logarithmically in frequency, or in other words, if I wanted to increase at a constant rate in pitch, I would have to increase at an exponential rate in frequency. So let me make a different kind of chirp. A chirp that starts at 220 hertz, and ends at 1680 hertz. And that takes a linear increase in pitch over an interval of 3 seconds. So this is a little different. This one, the one we just did, went linearly in frequency. But this one here is going to go linearly in pitch. So one such function, well, actually there's only one. So the function f of t should be 220 times 2 raised to the time over 3. Okay, so let's see. So that would it'd be 220 times 2 to the t over 3. Actually, I think 2 to the t would do it, not t over 3. Let's check. So when t is 0, we're at 220. When t is 1, we're 1 octave up. When t is 2, we're 2 octaves up, so that's 880. And then when t is 3, we're 3 octaves up. Okay, good. So this does it, actually. This goes over the range we want. But it does so exponentially. Okay, so we can ensure that we will hear a linear shift in pitch. All right. Now I need to integrate this in order. Again, I forgot to put this, but this is what I want my frequency contour to be. This is how I want the frequencies to move in time. In order to get back to my f of t, I have to integrate this. And I can do that by using some rules of integration, but it's a little bit messy, and there's something kind of neat that we can do if we use a numerical trick. So if you remember back to your calculus classes, you can numerically estimate an integral by putting a bunch of rectangles under the function, right? So we can do that actually with the function in, with the help of a function in Python called cum sum, cumulative sum. So if I said that my derivative of f, my instantaneous frequency, is 220 times 2 raised to the t, I can then integrate that numerically by saying, well, this is a cumulative sum of a bunch of rectangles. So I'm going to add a bunch of rectangles. The base of the rectangle is the interval of time. So this is how much time has elapsed between each sample. And then I'm going to multiply that by what the function is I'm trying to integrate. Okay. So this is how you can do, this is an integral numerically in Python using rectangles. So not the best numerical integration scheme, there are better ones. But this is fine to get started. So now let's listen. We'll say y2 is equal to mt dot cosine of 2 pi f, this thing that we just numerically integrated. y2, okay, so let's listen. All right, so here's the original. So you can hear, particularly when it gets to high frequency, it's not really moving that much in pitch. Okay. Whereas this one, we should move every second, we should move an octave. Okay. So you hear this moved at a different rate, but it ended in the same place. So if you really pay attention to 1, 2, and 3 seconds, you'll hear you're at an octave at 1, at 2, and at 3. Okay. So cool, that actually worked.